Welcome to the CompTIA A+ Prepcast presented by baremetalcyber.com. Cloud computing is defined by several essential characteristics that distinguish it from traditional infrastructure models. These features include elasticity, metering, on-demand access, and resource pooling, all of which work together to deliver flexible, scalable, and efficient services. The A+ certification requires a foundational understanding of these terms to help technicians recognize how cloud technologies function in real-world environments. Mastery of these core concepts supports effective troubleshooting, cost analysis, and service configuration across cloud-enabled networks. Elasticity in a cloud environment refers to the ability to automatically adjust computing resources to meet real-time demand. Resources can be scaled up when usage increases, such as during peak traffic periods, and scaled down when demand drops. This dynamic adjustment occurs without manual intervention and supports both performance optimization and cost control. Elasticity ensures that users always have the capacity they need without paying for idle resources when they're not in use. Autoscaling is the mechanism that powers elasticity. It monitors specific metrics such as processor load, memory utilization, or network activity, and adjusts virtual machine instances or containers accordingly. Autoscaling is commonly implemented in infrastructure as a service and platform as a service environments, where it enables web applications, back-end services, and databases to handle fluctuating workloads efficiently. The process is policy-driven and configured to react automatically, reducing the need for human monitoring and manual scaling. Metering refers to the cloud provider's tracking of resource usage, including compute power, storage space, and bandwidth. These usage metrics form the basis of billing, enabling the pay-as-you-go model that defines modern cloud service offerings. Technicians can access usage data through dashboards or APIs to monitor performance, track costs, and identify opportunities for optimization. Metering provides accountability and supports financial planning by giving clear insights into how resources are consumed. Transparent billing allows users to associate costs with specific services, projects, or time periods. This granular data enables accurate budgeting and forecasting, helping organizations avoid unexpected expenses. It also aids in identifying anomalies such as sudden usage spikes that may indicate misconfigurations or unauthorized activity. By understanding where every dollar goes, organizations gain control over their cloud investments and can better align spending with strategic goals. On-demand self-service allows users to provision and configure cloud resources without needing to contact the service provider. Whether deploying a virtual machine, allocating storage, or launching a database, users can take action immediately through a web portal or command line interface. This empowers teams to build and test systems quickly, accelerating development and reducing reliance on traditional procurement processes. Self-service is foundational to cloud agility and user autonomy. Resource pooling is the cloud provider's method of delivering services to many customers using shared infrastructure. Virtualization allows multiple users to access computing power from the same hardware while maintaining logical separation. This multi-tenant architecture ensures efficient use of resources, supports scalability, and reduces costs. From the user's perspective, resources are abstracted. They do not know or control the exact location of the servers they use, only that performance is guaranteed. Redundancy is the duplication of systems and services to protect against failure. Cloud providers use redundancy to distribute components across multiple availability zones or geographic regions. This ensures that if one server or data center fails, another can immediately take over. Redundancy may involve automated failover, data replication, and load balancing to maintain continuous service delivery even under adverse conditions. It is a critical component of high-availability architecture. Cloud platforms offer various types of backups and recovery tools. These may include scheduled snapshots, continuous data protection, or full system image backups. Backups are often stored in geographically separate locations to provide resilience against local disasters. Recovery features enable users to restore data quickly in cases of accidental deletion, data corruption, or ransomware attacks. These capabilities support both business continuity and compliance with data protection requirements. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Fault tolerance is the ability of a system to continue operating even when one or more components fail. It differs from redundancy, which refers to having backup components ready to take over when the primary ones fail. Fault-tolerant systems are designed with built-in resilience that allows them to absorb failures without service interruption. Redundancy supplies the spare capacity, while fault tolerance ensures seamless operation. Together, they form the foundation of a resilient cloud architecture that maintains uptime and reliability. Scalability refers to a system's ability to handle increased workloads by adding resources. Vertical scalability involves enhancing the capacity of existing resources, such as increasing memory or processor speed on a virtual machine. Horizontal scalability means adding more instances to share the load, such as deploying additional web servers behind a load balancer. Both types of scaling help cloud environments respond quickly to demand without requiring physical infrastructure changes, making them vital to performance and availability. Elasticity is closely tied to scalability, but focuses on the automation and flexibility of adjusting resources. In traditional environments, increasing capacity requires manual effort, such as upgrading servers or changing configurations. In the cloud, resources can be resized almost instantly. This removes the need for over-provisioning, where systems are built larger than needed just in case demand increases. Elasticity ensures that cloud environments remain efficient, cost-effective, and adaptable. Application Programming Interfaces, or APIs, allow cloud services to be controlled programmatically. Using scripts and automation tools, technicians can deploy systems, manage resources, and monitor performance without manual intervention. APIs are central to DevOps workflows, enabling integration with source control, continuous deployment, and monitoring platforms. This automation accelerates service delivery and minimizes human error, supporting fast-paced development and scalable operations. Geographic distribution in cloud computing places resources in multiple physical locations. This reduces latency by bringing services closer to end users and supports compliance with data residency requirements, where data must remain within specific countries or regions. Geographic separation also enhances disaster recovery, ensuring that services can be restored quickly from unaffected locations if one region experiences an outage. This distributed model is key to global cloud reliability. Service level agreements, or SLAs, define the expected performance, availability, and support commitments of a cloud provider. SLAs may specify minimum uptime percentages, response times for incidents, or maintenance windows. Many agreements include financial penalties or service credits if the provider fails to meet defined targets. Reviewing the SLA helps customers choose providers that align with their business needs and risk tolerance. Logging and auditing features are standard in cloud platforms and are critical for security, compliance, and performance monitoring. Logs track who accessed resources, when changes were made, and what actions occurred. These records can be reviewed to detect misconfigurations, unauthorized activity, or performance issues. In regulated environments, auditing is essential for proving compliance and supporting investigations after incidents. Elasticity contributes directly to cost savings in cloud environments. Since resources are only allocated when needed, organizations avoid paying for idle capacity. This model is especially beneficial for workloads that fluctuate, such as development environments, seasonal services, or applications with unpredictable usage patterns. Elastic environments can automatically scale down during low-demand periods, reducing overall spending without impacting availability. Centralized management tools allow administrators to control cloud resources from a single interface. These tools provide unified dashboards for configuring, monitoring, and reporting on infrastructure, applications, and user access. Centralization improves visibility, simplifies security enforcement, and reduces administrative overhead. For technicians, having one platform to manage everything streamlines operations and supports efficient troubleshooting. To summarize, key cloud features include elasticity, metering, redundancy, scalability, and centralized management. These features differentiate cloud computing from traditional infrastructure and allow organizations to operate with greater flexibility and efficiency. Understanding these terms helps technicians configure services, manage costs, and respond to changes in demand. The A+ exam may test these concepts through definitions or scenarios, so a solid grasp of each is essential for success in both certification and day-to-day IT support. Thank you for listening. Please visit baremetalcyber.com for more cybersecurity information, podcasts, books, and more.